So I'm audible?
Yes, sir, you are.
Okay, thank you. Yeah. So let me start with slide 41. That's where we had stopped. And okay. All right. So we had stopped at slide 40, where we were just looking at how function calls and returns work and the layout of the stack. So we reached this step where the main function has just called this function foo, and the local stack buffer has been, the local activation record has been laid out, and the stack buffers have been allocated on the stack. Okay, so now let's look at a couple of important entities. I think let me just video the video. The return address that is stored in the stack is a very important aspect of ensuring correct operation of the program. So if you tamper with this return address, you can essentially change the way that the program's control flow goes. So let's look at a simple benign example of what happens when you tamper the return address that's stored in the stack. But before that, let me just tell you about this ret instruction and the leave instruction. Okay, so the leave and the ret instructions. If you go and look at the virtual machine, and if you look at the disassembly of foo as well as main, you will find these instructions leave and ret appearing towards the end of each of these procedures, or the point where the procedures actually finish their operation with that return control. Okay, so if you open this function call example, study the assembly code for foo, you will find that these are the last two instructions. Okay, so leave and ret. So what do they do? Let's just try to understand their core functionality. Okay, so the leave instruction and the ret instruction essentially do the following, right? So when main calls foo, the stack looks like the left side of the picture, and when it finishes, it's supposed to be restored to this original state where the EBP now points to the base of the stack frame of main, and ESP points to the top of the stack frame of main. That's the right hand side of this picture. So control also needs to be returned to this function foo from main, which means that the instruction pointer now needs to go from this function foo all the way back to the instruction just following the call foo instruction in main. Okay, so that's the return address. So all of these things need to happen when the function foo finishes execution, and you need to clean up. So that's exactly what leave and ret do. As I was saying last class, the x86 instruction set is incredibly rich, which means that there are multiple ways of expressing the same functionality. And it just so happens that leave and ret instructions encode a set of functionalities that you can probably encode using a set of other instructions as well. Okay, so the leave instruction in foo essentially does two things, right? It restores the value of EBP to the value that's saved on the stack. Where is it saved? Well, right here on the stack, just after the return address. And it pops the saved return value from the stack and essentially cleans up the stack. Okay, so that's what the leave instruction does. And the ret instruction does the same for the return address. So it changes the processor's control to the return address that's stored on the stack, and it pops the return address from the stack. Okay, so when I say that it changes the processor's control to the return address, essentially there is another register called EIP or RIP in the case of x86-64. That's the instruction pointer. So the value of that instruction pointer is stored in this register. It now changes to this value that's stored on the stack. Okay, so when both these instructions execute, the stack is restored to its original state. All right, so now what we'll do is we will actually play with a fun example, and I will switch control over to this virtual machine, and we will see the power of return address modification. Okay, so let's look at this program on the slide for just a second, and then we will switch over to the virtual machine. So what you see are two functions in front of you, right? And these are implemented in this function called benign return address modif.c, that virtual machine. We will switch over in just a second. So the code shown there is roughly what is shown in the left here. Okay, and what you see on the left is pretty much two straight line programs, right? No conditionals anywhere. There's no if then else, there's no loop, there's no go to statement, nothing, right? If you look at main, it's a bunch of statements that start from index, flow straight down to the printf, and same thing in the foobar, right? There's no funny business here with any change of control with conditional statements and so on. Okay, so if you run this program, if you run main, what do you expect the output of this printf to be? Well, you look at the statement just before the printf, x is being assigned to 1, and printf should print the value 1, right? So let's compile this virtual machine, and as you can see on the slide, the output is actually 0. Right? So we would like to understand what it is that's going on over here that causes this thing to be 0. Okay, so let's do that. Let's start the virtual machine. Okay, let me share my screen with the virtual machine. Okay, there you go. I hope the virtual machine is now visible. Okay, so let's go to benign return address modification. And as you can see, it's pretty much the same program, right? I mean, yeah, it's exactly the same program. Okay, but if you run it, the output is 0. You expect it to be 1, but it's actually 0. So what's going on, right? So in order to understand what's going on, right, the only funny business over here is this function foobar that's being called from main, right? If you remove that call, in fact, you will see that main prints 1. It doesn't print 0. Okay, so the funny business, whatever funny business is happening inside foobar. So let's go and see what's happening inside foobar, right? So in order to do that, you have to disassemble foobar, and I've done that already. So you can go to assembly. Let's go to foobar. Okay. Uh, all right. So let's see what foobar is doing that causes the output to change value to uh, to 0. Okay. So what's going on is that so foobar. Let's see how many arguments did it take. I believe it took one argument. I forgot. Yeah, it took one argument. Okay, and it's allocating a character buffer of size 8. Okay, all right. So if you look at this code right here, and I will shortly switch over to the slides where I actually interpret the assembly. Okay, so it's a bunch of stuff that's going on over here, right? So what you see, this particular statement, this sub 18 hex ESP, is that it's allocating space on the stack for this local buffer, and then there's something that's going on with the GS segment register. That's not really important over here, but it's doing some stuff, and at some point it is so it's not a very long function, right? You can see that there is leave and ret, but what you can see is that so these are the key instructions, right? You're adding so you can see that you see this add instruction. It's add 18 hex to EAX. So what is 18 hex? So 18 hex is nothing but 24, the integer 24. Okay, so you can see that it's adding this value 24 to EAX, which corresponds to the source code to this statement called ret equal to buff plus 24. Okay, so you can stare at the assembly code. I would encourage you to actually open up the assembly code and follow along as I now switch to the slides and then tell you exactly what's going on. So let me interpret the assembly code using the slides. Just a second. Okay. Sorry, just a second. I'm struggling to share things properly. There you go. Oops. Okay. Wait a minute. What can you share? What can you see on my screen right now? Can you see the PowerPoint slideshow?
Sir, it was visible a while ago, but yeah, it's visible now.
It's visible now. Okay, good. All right. Yeah. So, okay. So these slides, let me just skip over uncommenting the call to foobar one and so on. You can actually play with those things at home. But let's just quickly look at what the stack looks like when main calls foobar, right? So it looks like pretty much what is shown here on the site. You can work out the exact size of this of the stack frame by looking at the value of what ESP subtracted. I believe it was 18x. So it would look like what is shown over here, and the difference between the values of ESP and EBP is 24. Okay, yeah, so that's 18x. So why is it 24? Right? I mean, you can actually reason about this, and in this particular case, the compiler is doing no funny business, so it's actually allocated space pretty accurately. So if you look at the assembly code of foobar and see the quantity that's subtracted from ESP, ESP is subtracted by 24 bytes. And I'll leave it to you actually as an exercise to go and figure out why it's 24. Okay. So the value of EBP is actually saved on the stack, and you know that's a 4-byte value, right? EBP stores a 4-byte value, and that's saved on the stack. And the return address, you will find that it's actually located exactly 28 bytes away from ESP. Okay, so if you look at the source code of the program and you look at the assembly code of foo, you will locate the register that points to the beginning of buff. Okay, so what is the register that's pointing to the beginning of buff? Well, so actually it turns out to be EBP minus 14x. Okay. So how do you know that? Well, essentially you use the hint is the load effective address instruction. That is, you know, when you see the source code, there is you're trying to load the address of buff somewhere, and so somewhere in the assembly code the corresponding memory operation must happen. That's what is happening over here. So it's load effective address of EBP plus 14 to EAX. Okay, and so the address of buff is essentially 20 bytes, or that's 14 hex below EBX or EBP. Okay, that address is stored in EAX. Okay, so the next instruction in your assembly language sequence says essentially add the value 24, which is the integer 24, which is 18x to EAX, which basically adds this value. So that's red equal to buff plus 24. Okay, so what stack location does the new value of EAX actually point to? Right, so if you look at what EAX is actually pointing to, it is pointing to the return address. Okay, since the value of EBP is 4 bytes long, this is the EAX is actually pointing to this source variable that is read in the program, right? So the source variable read actually takes on the address of the return address that's stored on the stack. Normally, you don't play around with the return address like this, but this is just sort of an example to see the power of return address modification. Okay, so I encourage you to actually open up the virtual machine and follow along. You can replay the lecture and follow along the assembly code together with exactly this picture over here. Line by line, you can actually follow along, and you will see that the source variable read actually points to this return address. Okay, so the next instruction in the program actually increments the value that's stored the address pointed to by ret, which is star ret, in this particular case the return address, by 8. Okay, so you're adding 8 to the return address, and what this effectively does is that when this function foo returns, it causes the program to return to another location. So which location? So ideally this return address must return to the statement x equal to 1. Right? X equal to 1 is exactly where this foo bar must return to once it's finished its operation. But because you added 8 to this return value, now the function foo bar, once it finishes its job, the processor is going to return to another location in the program. Okay, so which location? Well, so go look at the assembly code for main and locate the call to foo bar. Okay, the original return address must have been at the start of the address just following the call to foo bar. Okay, that is basically this address 80484C5 in hex. Okay. So what does that instruction do? Well, it seems to be moving the value 1 to this ESP plus 1C hex. Okay, what is this ESP plus 1C hex? Well, it's the place where the variable x is stored in the stack entry of main. It's the local variable x in the stack frame of main. Okay, so this move instruction, it's actually corresponding to x equal to 1, the source code line x equal to 1 in the program. Okay, so by incrementing the return address by 8 bytes, we are asking the processor to return to the instruction 80484CD instead of this 80484C5. So you're effectively asking the processor to skip over this instruction x equal to 1. And as a result, when the processor returns, this x equal to 1 has never executed, right? The processor never actually executed the statement x equal to 1. So the value of x remains unchanged. And as a result, printf prints the value 0. Okay? So that's what is going on over here. Now, this example that I've shown you is fairly benign, right? I mean, this is not really a buffer overflow. In fact, there was no buffer overflow vulnerability in this program at all. All we did was we played with return addresses by changing around return addresses, actually adding a constant value and so on. But what it went to show you is that if you play with the return address, you can actually go and change the control flow of the program and make the program behave in unexpected ways. Okay, and that is key. Okay, so you can try all sorts of experiments now. This virtual machine is yours to play with. So you can go and change the return statement star ret plus to various other values. Go try star ret plus equal to 24 and recompile the program and run it. Okay, you can change this statement ret equal to buff plus 24 to other values. Just go play with it, right? In fact, what I would encourage you to do is do the following. Go to foobar, add a bunch of more local variables, right? Instead of char buff of 8, go add another, make it char buff of 16 or go add another buffer. Recompile the program, look at the stack layout, and then go and figure out exactly what this ret equal to buff plus 24 must change into, right? How many bytes should you change it by? And go figure out, what ret plus equal to 8 should be, right? Should it still be 8, or should it change to another value? Go change the main function as well. This is how you go and get comfortable with assembly language, right? Go play around with the program, see what happens, disassemble it, see it, and then try to reason about the behavior of the program by just single stepping through the program's execution. You can do that within GDB. And if you have not actually tried GDB yet, or you're not comfortable with GDB, I suggest that you actually go and spend some time with GDB. It's a very useful tool. And there are plenty of man pages and instruction manuals available on the internet. Go get familiar with GDB. It's a very, very useful tool. All right. So what this example just showed us was the importance of the return address, right? It shows you how important the return address is on the stack and how it determines the control flow of the program, right? So if you were to go and change the return address, or if an attacker were to go and change the return address, you can actually mess up the execution of the program in totally unexpected ways. Okay, so in this particular case, you did something probably harmless, right? You went and skipped over this x equal to 1. But what would happen if you let the attacker control the return address stored on the stack? Can you really do something much, much more dangerous, right? So let's try to go and find out. So let's look at this program. It's a small variation of the program that we have been studying so far, except that the function body of foo has changed. Okay, so in foo, you've got a fixed like stack allocated buffer. It's 8 bytes long, and you've got a gettr statement. Right? What does gettr do? Well, it just reads from the command line till you see the carriage return, and then it fills up the buffer with all of the stuff that you obtained from the command line. You can also replace this with a statement that, for example, reads from the network socket, and maybe this is a network-facing program like a browser or some other network debug, and it fills up the buffer with that value. Okay, so now what happens, right? So now what happens is that because getters does not do any buffer bound checking and it just fills up the buffer with all the bytes that it gets from the command line till it encounters the carriage return, it allows the attacker to enter data into this buffer and just keeps writing into this buffer until it encounters the carriage return. Okay, so what does that mean, right? So the write starts off with this location over here and buff, and imagine the internal operation of getS. All it's doing is that it's reading one byte at a time and it's doing pointer arithmetic, right? It's saying, okay, p equal to p plus 1, now get me the next byte from the command line, fill that location, and then do this in a tight loop and break the loop only when you see the carriage return. Okay? So what does p equal to p plus 1 actually correspond to in this picture? So if your pointer is pointing right here, where my arrow is pointing to in the beginning of this buffer, right? What essentially happens is that p equal to p plus 1 would move up the stack, up the stack, up the stack, and keep moving up. That's how pointer arithmetic goes. Remember, the top of the stack over here shows you the higher addresses, and the bottom of the stack shows you lower addresses. That's how stacks are laid out. So when you add a positive value to a pointer, it's actually moving up. Okay? So what this ends up doing is that you keep writing into this buffer, and the attacker actually controls this, the value of this pink location over here, this pink stuff that I've shown over here, and the attacker can go and override the return address. Okay, so he can go and change the return address and make it point to whatever he wants it to point to. Okay, thereby completely messing up the control of the program. Okay, let me just continue. So what would the attacker override the return address with? Any ideas? What's an attacker's goal, right? So the attacker's goal, if you remember from last class, it would be to try to get the privileges of the program, right? I mean, get the program to do whatever the attacker wants it to do or the program to do. So in the worst case, let us say that this is spawning a shell with the privileges of this program. So how would you go about doing that? What would you override the return address with to spawn a shell? Any suggestions? Any ideas? Please raise your hand.
We need to fork a shell.
You want to fork a shell? Yes, you want to spawn a shell. Not really fork, you want to spawn a shell. Yes, Sushant. Oh, sorry, Shashank.
Sir, we can use commands like exec v or exec, all the exec family, any of the exec family, and pass the address to the shell. And
but where
in that way,
these commands?
We can use the buffer itself for storing our commands.
Okay.
And then
great.
Yeah.
Right. So that's the idea, right? So the idea is that the attacker now wants the program to execute commands of the attacker's choosing and change the return address to point to these commands. But where will these commands be placed? Well, remember that this buffer is completely in the control of the attacker. So the attacker can fill up this buffer with the hexadecimal representation of all of the commands that he wants the program to execute, which, for example, in this particular case would be to spawn a shell and change the return address to point to the first instruction that he just inserted. In other words, he goes and fills up this buffer right here shown in pink with the contents, with the contents of this buffer would be the hexadecimal encoding of the instructions to spawn a shell or do whatever the attacker wants to do and change the return address over here to point back into this buffer to the first instruction that corresponds to this instruction sequence. Okay, so then what happens is that when this foo returns, the return address points to the first instruction that the attacker inserted, and then that's where control resumes. Right? So in the normal case, you would expect control to resume somewhere in the code segment of the program. Remember, it's a big process. The code is loaded somewhere else in this program's address space. But no, in this particular case, the return address is going to point to this buffer, and the buffer contains the instructions that the attacker injected into the program's address space. Remember, all of this code that the attacker now wants to execute doesn't exist in the program's address space. He's making up these instructions as part of the input sequence that he's giving. He's encoding it in hex and then inserting it to this buffer and changing the return address to actually point to the within the buffer itself. This is the simplest version. I'm going to talk about more complex variants later on. But that is how the attacker will get the program to do whatever he wants this program to do. Okay, so the stuff that he inserts into this buffer over here, the attack code that he inserts into this buffer over here, is actually called the attack payload. And what we are going to do for the next 20 minutes or so in the next few slides is actually understand how attackers create this payload. Okay, so this is called payload engineering, right? So you are a bad guy, and now you found this buffer overflow in the program, and now you want to go and exploit it. How do you go about creating this exploit sequence? So this Aleph null paper that is the assigned reading, it actually talks about how you create this payload, right? It's the payload engineering part that really changed the game here, right? In the sense of making this attack a systematic one that anybody who has read the paper can replicate, including yourself. Okay, so we want to write an exploit program, and the exploit program that we want to write pretty much has to mimic what I've shown you in the slide over here. Okay, so this particular exploit program that I'm showing you on the slide over here has a main function and so on, but let's ignore the main function for a second. Let's just focus on the three statements starting with name0 equal to /bin/sh. Okay, so this is how you spawn a shell. In fact, you can go and try this. You write this program and then you write the code exactly as shown over here and you execute it. When you run this program, you'll get a shell. Okay, so what are you doing over here? Well, actually, you'll have to change the /bin/sh to point to the path name of the shell on your particular machine. On this virtual machine, I don't know what that is. You'll have to go and check what it is. But whatever it is, you have to just change that string. Okay, if you do that, this will spawn a shell. And what's the magic sauce over here? Well, the magic sauce is this exec v instruction that's actually taking these arguments and in this particular order, spawning a shell. Now, exec v is actually a library function that's implemented in libc. Ultimately, it makes a system call, and we will see all of that in the next few slides. What I want to mention right away over here is that this is not the only way to spawn a shell. Right, exec v is one library command, and I'm going to actually follow through by compiling this program and looking at the disassembly. There are other ways to do it. There are other variants of the exec family, and you can play with all of them. It just so happens that this particular variant, exec v, takes these three arguments. Right? What are these three arguments? Well, the first one is a pointer to this string, to the first character of the string, bin/sh. So that's name of 0. The second one is a pointer to this name array. As you can see, this name array should contain the first element should be /bin/sh, and the next element is just null. Okay, and the third argument over here is null. You're not using it; it's just null. And so, if you do exactly this sequence, you will get a shell. You can go play with exec v. Just go do man exec v, and you will understand the meaning of these arguments, what each argument stands for. But this particular way of using it spawns a shell. Okay, so when you compile this program, this is the disassembly that you see. Okay, so caveat over here, if you go and compile this particular program on your virtual machine, this might not be the exact code that you see. I compiled this program on another virtual machine whose image I don't have right now, but this is what I got, and so I put that over there. But pretty much if you compile it, you'll see something similar to this. So don't compile this program on your virtual machine and then sort of be surprised when you don't see the exact addresses or the exact sequence of instructions, right? It's just supposed to be instructive. It's not supposed to be an exact one-on-one replica, but you'll see pretty much like this, okay? So the interesting part over here, of course, is the call to exec v, right? You see this instruction, the call to __ exec v. That's when the exec v instruction in the library, the standard C library is called by this main function. And before that, you can see that the three arguments are being pushed. The first argument over here in this movl pushl just before the call, the second argument with the leal and the push, and the null value, the third argument is being pushed over here. The push 0. Okay, so the interesting bit, of course, happens with the exec v. So we have to actually go and examine what happens with this call to exec v. So let's go do that. So where does exec v reside? Well, exec v actually sits with the standard C library. which is loaded into every program's address space. Okay, so it's loaded either statically because you statically compiled your program and linked it with this libc, okay, or it's loaded dynamically. This is dynamic linking of libraries where you see the call to the execve. The code for execve does not exist when the program sits on disk, but as the program starts executing, the dynamic linker brings it, loads it into this program's address space, and then patches up the offset table, and then you end up calling this execve. Okay, so if you have, what this requires is a little bit of understanding of dynamic linking. If you're not familiar with dynamic linkers, don't worry too much about it. You can just think about this program calling execve somehow. But you should go and look up dynamic linking. It's actually a fascinating piece of engineering. And we cover it in a little bit of detail in the operating systems course, though not in very much detail. But essentially, this code doesn't exist when this program starts. It's patched up at runtime by bringing the library into the program's address space. Okay? But we'll assume that the library is being loaded and that somehow this call to execve happens. Let's go and see what execve does, right? So here is execve. So now if you go and disassemble execve, this is what it looks like, right? So don't be surprised if you do an opt dump of your program on disk and you don't find execve over there. It might not exist. As I said, it's brought in at runtime. The only way to go and examine it would be to go and run the program and then disassemble at runtime using GDB. You can do exactly what you do with opt dump with GDB as well. It's called disassemble. That's the argument within GDB to go ahead and sort of look at the code. Okay, so what's going on inside execve? Well, a lot of stuff is going on inside execve. We don't really care too much about what's going on inside execve, but there is one instruction that we are really interested in over here, which is this int instruction. Okay, so if you see, it is the 4, 5, 6, the 8th instruction from the top, int 80. Okay, int hexadecimal 80. Okay, and also interesting for us are the 4 instructions that precede this int 80, which is movl 0xbeax, movl ebp plus 8 to ebx, movl ebp plus c hex to ecx, and movl ebp plus 10 hex to edx. Okay, if you want to compile this on a x86 64-bit machine, it's going to look slightly different. In fact, instead of int 80, you'll see this instruction called syscall. So that itself should give you an hint what's going on over here. So this int 80 is the way in the x86 32-bit instruction set to do a system call. Okay, so what is a system call? Right? A system call essentially tells the processor that it needs to switch its mode of execution from user mode to system to kernel mode of execution or supervisor mode of execution. And now the operating system kernel, which as you remember from the earlier part of this lecture, is actually loaded into the processor's address space, the top 1 gigabyte. Okay, now the operating system takes over and then does something. So obviously the operating system is doing something on behalf of this program, and the program is to tell the operating system what to do. This particular case is execve. That's why the program executed this int 80 instruction. It is to execute this execve system call, in this particular case, not the library function, the system call. And so now you need to pass the arguments, and that's exactly what these 4 move instructions before the int 80 instructions do. Right? So in the very first instruction, this movl 0xbeax, you're actually telling the operating system which system call to invoke. So on Linux, there are around 300 system calls, and every system call has a number. Right? So what you see over here is that it's the 12th system call that's being invoked, 0xbeax. This, of course, what number is passed depends upon the precise version of the kernel and so on that you're working with. In this particular case, 0xb corresponds to the instruction that actually implements the equivalent of exec. Okay, and the next 3 arguments are the arguments to exec. Okay, and this particular calling convention over here, this copying stuff into this registers EAX, EBX, ECX, and EDX, is the way that the operating system, the system call implementation with the operating system, expects arguments to be passed. This is not to say that system calls can only take 4 arguments. They can take more arguments. and there's a different convention to sort of pass those things. But this particular case, you are expected to pass these arguments via these four registers. Okay, so now I'm not going to look at the code of the operating system, but pretty much this is what happens, right? You need, this is what the attacker can do, because this is the stuff that the attacker needs to insert to the program's address space. The operating system code is not really available to the attacker over here. So this is all we need to understand from the perspective of payload engineering. If you want to design a payload, it suffices for you to now go and understand what this code over here is doing and try to replicate its functionality. Okay, so in the next few slides, what I'm going to do is that I'm going to abstract away from this assembly code that you see over here, write down the English language specification of what exactly you need to set up on the stack to create the payload. And then from that English language specification, we will work our way down back into assembly. Right now, we are seeing code as it exists in the standard C library, but now we are going to recreate this code from scratch and create the attack payload. Okay, so here is the English language requirement of what you need to do. Okay, so what it says is that in order for you to create this payload for the attack, you need to have this null terminated string called /bin/sh somewhere in your program's memory. Exactly where, we don't know yet, but you need to have it somewhere in memory. You need to have the address of the string in memory followed by the null long word. Okay. Why is that? Well, if you go back 2 slides, you'll see, right? The way that this name buffer was set up was this /bin/sh, which is null terminated, followed by the null long word. Okay, so you need to set it up exactly as you see in this particular program. Okay, you need to have that. You need to copy this value 0xb in hexadecimal to EAX. Why is that? Well, we saw that in the previous slide, right? This is the hexadecimal encoding of the number of the system call exec that you want to execute. And the next 3 arguments are essentially arguments that you pass to exec, right? The 3 arguments to exec are passed like this. You copy the address of the string into EBX, you copy the address of the string again into ECX, and you copy the address of the null long word into EDX. Okay, this corresponds to the 3 arguments that you saw in exec B, name of 0, name, and null. Okay, that's how you call exec. And then you have to execute the int80 system call. Okay, so if you somehow were to write shell code that implemented these basic English language requirements that I said, and let's go back over here to this particular slide. If you were to write that down in hexadecimal and you were to fill it up into this pink buffer that's shown over here, and then override the return address to point to the first instruction, which is in this particular case, I would say the instruction copy 0xb to EAX. If you were to, in fact, there's some more stuff that comes before it, you will see in a second. If you were to change the return address to point to the first instruction of this attack payload, your task as an attacker is done, right? Why is that? Well, when foo returns, the return address will just go and point to this first instruction in this payload that you just created. And then lo and behold, the processor does its own task. It just goes and executes this particular attack sequence over here. And as a result, you will get a shell with the program's privileges. If this was a setuid program, you would get a root shell, right? Mission accomplished. Okay. So now it's our job to go and figure out how to take these English language requirements that I just said and compile it down into actual working code. So let's go see that. Okay. So here's your attack payload. Okay. I just took what I wrote in the previous slide in English and I've converted it line by line into assembly. Okay, that's all I've done. Okay, if you're with source code, you can write source code and then figure out how to write that source code in assembly. But all I've done is a line by line translation of the previous slide in English to assembly. Of course, there are a few things that are unknown in this assembly. Okay, I do not know where this string is stored in memory. I do not know what its address is. So I'm going to represent all of those things using variables. Okay, so that's string adder, So all I'm saying is, look, move the string address into this variable called string adder. Move this byte 0xb to this null byte adder, move L0x0 to null adder, and so on. Okay. And then there is this int 80. There are some cleanup instructions over here. I would not worry too much about them right now. This is just directly from your from that paper, the Aleph null paper. But all we need in order to implement the attack is the first int 80 as well as the stuff that comes before it. Okay, and the /bin/sh. Obviously, now you're the attacker. You have to somehow put the /bin/sh string, the value /bin/sh somewhere into the program's memory. Where do you put it? Well, you put it into this buffer, right? So you write down the bytes corresponding to the /bin/sh somewhere in this string, and then you put it over there. Okay. So where in the process of where the process address space is this stuff over here going to be placed? Well, it's going to be placed in the buffer, but the attacker does not know the address of the buffer a priori. So how do we go and now fill up the values of these variables, right? Because at this point these are all unknown, right? And I cannot make this attack payload essentially work portably across different versions of this program, because every time I have to go and customize this. How do I make this attack payload work? Well, so actually, if you go and see this this paper, Aleph null, it not only contains the tricks to make the attack work and write these attack payloads, it also contains a number of cool engineering tricks. And one of these cool engineering tricks is this thing called relative addressing that I will explain in the next slide. Okay. So I've just compiled this program a little bit more, but what you will see is that I have added a couple of instructions. So I'm going to switch back and forth between slide 63 and 64 and show you the new stuff that I've added. Okay. So if you see the first instruction, move L, string adder, all I've done is that now that becomes the third instruction over here, move L, ESI, array offset, ESI. Okay. That's all I've done. Okay. And then everything else, move B, move L, and so on, it's going to be a one-to-one translation of all of the other instructions over here, except that I've replaced the string adder, and so on with actual registers and offsets. Okay. And of course, the /bin/sh goes right at the end. And what you will see in this new assembly language sequence is that I've inserted 3 new instructions. Let me just go over them quickly. First instruction is this jump offset to call, which is the first instruction. The next instruction is pop LESI. And the other new instruction that did not exist in the previous slide is this instruction called call offset to popl, that is just before this /bin/sh string. Okay. Everything else is just a one-to-one translation. Okay. And what you see in this particular slide is that you also see the size of the instructions. So one of the things about an instruction set like x86 is that instructions come in different sizes. Okay. This is a complex instruction set architecture, or CSIC, and the instructions over here come in different sizes. And so what you see over here on the right hand side after the comment sign are the size of each one of these instructions. So the jump offset to call, what is offset to call? Well, offset to call is actually a string that I use, but you can replace it with an integer value. What is offset to call? Well, it is the distance to this call instruction that you just see before the /bin/sh. And what is that distance? Well, you can actually calculate it by adding up the bytes corresponding to the length of the instructions. So 2 plus 1 plus 3 plus 4 plus 7 and so on. If you add, you'll get a number. You just have to put that number in hexadecimal over here to this jump. So you can jump by relative addresses too, and that's what this is. Okay. And same thing over here, right? This call offset to popl, right? So this popl instruction is a second instruction. So you can also just, instead of calling by an absolute address, x86 also supports calling by relative address. So over here, the offset to popl is just the number of bytes that separate this call instruction and the popl instruction. It's a negative offset over here. So you just have to write down that number and put it over here together with this call. And when the processor executes it, it's going to call it by an offset. So it's actually a very clever trick. Let us go and see exactly what happens when you execute this instruction. This instruction sequence rather. Okay. So let's go walk.
Sir, I'm sorry to interrupt. Yeah,
Yes,
just
please
wanted
go
to
ahead.
let you know that your mouse pointer is not visible to us, at least to me. If somebody is able to see, he can just say.
Oh,
But
I'm sorry.
yeah,
I was actually I had a doubt whether it was being visible or
yeah,
not. So
yeah.
that's why
So
I'm talking about like the fifth instruction from the top, the fourth
correct, correct.
instruction from the top, and so on.
Yeah. So when you're
I don't
saying
know.
here, we are not able to actually relate. So just wanted to let you know. Yeah.
Oh, okay. So let me stop sharing and then start sharing in a different way. Maybe I should share my entire desktop rather than just the presentation mode. Okay, just 1 second. Give me a second. I'll try to figure it out. Thank you for letting me know. You guys should just warn me in case something like this happens, so that I don't keep presenting and then
Yes, sir. Yes, sir. It is now
you
visible.
can see now, right?
Yeah, yeah, yeah.
Yeah. So this is a different way of. I just shared the entire screen, and I think this is better. Okay. Hopefully you can see my mouse pointer now.
Yes,
Yeah.
it is visible, sir.
Okay.
Yeah.
All right. Yeah. So let me just walk through this code. Hopefully now it should make much more sense with the mouse pointer visible. So let's walk through the instructions. The first instruction is the jump. Okay. Jump to the offset to the call. So what happens when you start executing it from the very first instruction? Well, control goes and changes. It goes to the call instruction. Okay. Now, what does the call instruction do? Well, it says call offset to popple. Okay, what does a call instruction do? Remember back to our discussion on call. Call does a couple of things, right? It pushes a return address on the stack and it changes the instruction pointer to go and start from the instruction that you have just given. Okay, so in this particular case, when this call instruction executes, what gets pushed onto the stack as a return address? Any ideas? It should be the instruction
Bin
following the
slash
call,
ss.
the address following the
Bin
call. Yes. Please go ahead. Somebody had something to chime in.
So the address of the string bin h gets popped onto the stack.
Exactly. Right. So the address of this string bin.sh gets pushed onto the stack. So that's the beauty over here, right? You do not have to know a priori where the address of this bin.sh is in your buffer. This call instruction is dynamically pushing the address of the slash bin slash sh because that in some sense is quote unquote the return address of this call, even though this is not an executable instruction, right? It's the address just following the call, and that's the address of the slash bin slash sh somewhere in memory. That gets pushed where? It gets pushed onto the stack. Okay. Then what do you do? Well, what did you call? You called which instruction? You called the popple instruction, right? That's the offset to popple. Your call instruction is just going to change the instruction pointer to go to this popple. Okay. So what is this popple doing? Well, it's popping the value from the top of the stack. What's the value on the top of the stack right now? It's slash bin, the address of slash bin slash sh. Okay. And what did you do? Well, you stored it in this register called ESI. That's what you did here. And now, lo and behold, I've got the address of this string slash bin slash sh. It's within this register ESI, and now everything else in my attack sequence that relied on the knowledge of this of the address of the string slash bin slash sh. Now I can do because the address of that slash bin slash sh string is available in ESI. And that's what the rest of the instructions are doing. Everything that is being done is just an offset from ESI. What is the array offset? Well, the array offset is, given this slash bin slash sh, where is the array starting? In this case, it's 0. Well, what's the offset of the null byte from ESI? Well, you know what the length of the string is. You can calculate the number of bytes. 1, 2, 3, 4, 5, 6, 7. The 8th byte is the null byte offset. Where is the null stored after the string? Well, it's stored after the backslash 0 of the slash bin slash sh. That's what this null offset is. So you know the values of each one of these variables that's in this program, and you can just fill it up, and you've got assembly language that is completely filled up. Okay, and there are no unknowns here. All you have to do now, of course, is to go and change the return address. Of course, that also you can insert into this attack sequence. But now the next piece of the puzzle, of course, is you have to convert this assembly language sequence into hexadecimal. because of course, you can't insert assembly language into your program. Your processor doesn't understand it. You have to insert assembly language. So how do you convert, how do you have to insert hexadecimal? How do you convert assembly language to executable code? What do you do? Any ideas? Every one of you must have taken a compiler class.
So you use obj down to get the hex code for it.
No. OBJ dump gets you assembly code from hex code. It's the reverse. What I'm saying is, given this assembly code, I want hexadecimal code, which is the executable code. I want to be able to produce the equivalent of an A.out that I can run. How do you go that way? How do you go the reverse direction?
Pass through assembler.
Use an assembler, right? An assembler, for example, AS or GAS or GASM. These are all assemblers that take assembly code, right, and produce an executable code. That's what you do. You produce to produce hexadecimal code. I'm going to show you how to produce this and sort of just take the output over here and then show you what it looks like. So when you, let's say, compile this stuff and produce the corresponding hexadecimal, it looks like the stuff that you see that I've put within this shellcode array over here. Okay, this \x just denotes that it's hexadecimal. But this stuff right here is something loosely similar to what you would see if you were to take this code that you just saw and convert it into hexadecimal. This is all just hexadecimal code. Your processor understands this. You can't read it, but that's what this is. And all this main program is doing over here, you can even ignore this main program, is that it is changing the return address over here to point to the beginning of this attack code sequence. But essentially, if you were to take this stuff over here that's shown in this within these quotes, and you were to put this within the string in the buffer in the program's memory, and you were to, let's say, change the return address to point to the first one, you would have a shellcode. Okay, so you can use GDB to create this, and you can sort of also use an assembler. But this is how you get the corresponding shellcode or the hexadecimal equivalent from the assembly code. Okay. So that concludes the attack. I haven't actually spoken about how to change the return address, but that is already an easy trick. All you do is you append more stuff to the end of this array or to the beginning of this array, and you change the return address so that it points to the beginning of this attack sequence. Okay, but there are a few other loose ends in this particular program. Yes, somebody has a question.
Yeah, it's Alvin. Yeah. I have a question in the previous slide.
Yes.
So why do we have to set the null byte and the null long word?
Yeah, those are, so when I say the /bin/sh string goes over here, remember, in that English language specification, I mentioned that the /bin/sh string actually goes over there with the null byte and the null long word following it. So it's following the /bin/sh. That's where those are placed.
Yes, so do we have to set it during the instruction?
Do we have to? No. Those are included into this thing over here as a literal. You can also set it if you want, but in this particular case, I'm just showing you how it's set as a literal. Yeah.
Okay.
Yeah. Okay. Okay. Let's move forward. Okay, so one loose end over here is that you see a number of \x00 characters in this sequence over here. That's actually bad. A \00 it corresponds to the end of the string, and these are inevitable. Sometimes when you compile this program, you'll see the \00 just emerging because of the encoding of these instructions. Okay, and if you have these string ending sequences within your shellcode, because you're reading from getS, it might end up terminating the reading the attack sequence from the command line and therefore not successfully carry out the attack. Okay, so it is your goal as an attacker to prevent this from happening. So how do you go about doing it? Well, the way you go about doing it is to put the x86 instruction set to work for you as a bad guy. Okay, so and what you do is that you take the richness of the x86 instruction set, where a result, where, as I told you, you can encode pretty much the same thing in different ways and avoid the presence of these so-called troublesome bytes. So, for example, I'm showing you this instruction over here: move B 0x0 0x7 ESI, and actually this should be move L, not MOLB. It should be move L 0x0 to ESI plus C. Well, another way to encode exactly the same functionality without actually explicitly mentioning the 0x0 over here is the following, right? You take a register EAX, doesn't matter what the contents of EAX are, and you XOR the register with itself. So what happens now? Well, the register contains the value 0 as a result of this XOR. And then you just copy the value of the register EAX into these into the corresponding ESI registers. ESI plus 7, ESI plus C. Okay, so over here, the encoding of this instruction sequence XOR move B, move L is now going to look different from the encoding of this instruction move B and move L, because now instead of passing a literal as an argument, we are actually passing a register. So that corresponds to a different instruction hex encoding in the Intel x86 instruction set, and hopefully you've avoided these troublesome bytes. Same thing in the next one, right? Move L 0xB to EAX. Well, if you see over here, the least significant bytes of EAX, which is a 4-byte register, are being affected. In fact, only the least significant byte is being affected. So another way of encoding it is using this move B instead of move L. Just move a single byte 0xB into AL. AL is an alias for the least significant byte of EAX. Okay. So as you can see, there are multiple ways of encoding pretty much the same functionality in the x86 instruction set. There's one more over here you can follow along. Over here, what I'm doing is moving 1 into EAX, moving 0 into EBX. How to avoid that? Instead of mentioning these literals, I just XOR EBX with itself. Move L EBX to EAX. So now EAX stores the value. So now EBX stores the value 0. EAX also stores the value 0, and then increment EAX. So now EAX stores the value 1. Okay. So very, very rich ways of doing this. In fact, this is pretty much what a compiler optimizer does. It takes a compiler backend, right? It takes an instruction sequence and finds a new instruction sequence that implements the same functionality. But in a compiler, of course, your goal is to reduce runtime or compile time or whatever it is, right? And produce an instruction sequence. Over here, your optimization goal is not to reduce runtime, but rather avoid these problematic bytes in your payload sequence. Okay, so you can play around with your assembly language instructions to produce different things. In fact, there are tools available to do this, right? Just like we use compilers, the bad guys have got a tool. This one particular famous example is called the Trident polymorphic engine. It's available in the underground economy for around $500 or something. So they have license fees and all that, just like real software. They also have a booming underground economy. It's $500 or so. You buy the Trident polymorphic engine and you feed it your attack sequence. Out come, maybe 1,000 or 2,000 different variants of exactly the same attack sequence. Okay. So why is this relevant? Why is this important? And why is the license fee for the Trident polymorphic engine $500? Well, the reason is because of the cat and mouse game between attackers and defenders. So how do you detect a buffer overflow exploit, right? So I told you about the Sasser worm, the Code Red worm, and so on. How did you go about detecting those exploits? Well, how does McAfee or Symantec or one of these so-called anti-malware companies go and detect these exploits? Well, the way they go about doing it is that they look at incoming traffic, let's say in your laptop or at the network gateway, reassemble the packets, and then check whether the packets contain a known attack pattern. What is this attack pattern? Well, the attack pattern will correspond to an actual payload sequence that was observed in the wild on the internet, corresponding to the payload sequence that exploited a buffer overflow in some target program. Okay, maybe your Internet Explorer or whatever it is. There was a particular attack sequence used to target a buffer and overwrite the return address. If they find that same sequence of bytes, they will flag that network packet as dangerous and then quarantine the application or quarantine that particular download that you just got. Okay, so this is called signature matching. And when you find that, you go and update your antivirus program's signature database as it does from time to time. that is exactly what you're updating. You're updating these patterns of observed attack sequences that the malware companies have observed over the last few days, and then they push and update your antivirus database. So it just does pattern matching of the network payload of the network traffic against this database and looks for exact matches. And now you can see how the attacker's job is all of a sudden become simpler, because you just create an attack once and then you create 10,000 variants of it, and then you launch these 10,000 different attacks. Now all of a sudden the task of the anti-malware company becomes 10,000 times harder, because now instead of producing one signature, they have to produce 10,000 signatures. And the attacker and defender can continue to play this game. As and when new signatures are developed, the attacker goes to a tried and polymorphic engine, gets a new attack sequence that implements the same thing, and then does it. So look at the attacker's job over here. The hard work of creating the attack sequence is done. Just once you do it, you figure out where the buffer is stored, you create the attack sequence, done. And now you take that attack sequence, pass it to this tried and polymorphic engine, or whatever polymorphic engine you're using. Out comes another attack sequence. Out comes another attack sequence, right? It's just a matter of pressing a button. But now imagine the anti-malware company's job, right? Now they have to actually place honeypots. We will talk about honeypots later in the semester. Go figure out or fingerprint the attack, pass this to their development teams that are actually going to painstakingly go and observe this attack, make sure that they extract the right signature from it, and then send it out, push it out to you, and hope that you go and apply that signature update. Not all of us update our antivirus engines all of the time and hope that they do it. So the attacker's game is really fast, and the defender's game is now not as scalable. And you can see over here how the richness of the x86 assembly language instruction set allows for easy polymorphism. This is called polymorphism, where you take one attack and create like gazillion variants of it that implement pretty much the same thing. Okay. And all of this is just done by moving around instructions that implement the same functionality. Okay. Okay. So we will talk about all of this, and we'll talk about like better ways to engineer malware detectors and so on later on in the semester. But yeah, I mean, so this in the process of eliminating attacks in the payload, we hit upon this idea that you can actually create different instruction sequences and fool malware detectors. And for a long time, in fact, this was the way that attackers work. If you go and look at your anti-malware database, it contains thousands and thousands of signatures. Are there really that many, vulnerabilities in the wild? Actually, there are 10x fewer, right? And this is because the attackers have discovered this trick of minimizing the work they need to do to go and exploit things in the wild. Okay. All right. So there are more advanced buffer overflow attacks. And what I'm going to do is, we will actually talk about some of these more exotic variants. And we will talk about in this lecture and the next one, we'll talk about some very basic defenses. And these basic defenses are the ones that are actually deployed in the real world. We will talk about this defense called WXORX. We will talk about ASLR and so on. And we will see that it's a cat and mouse game. Okay, as and when a defense is developed, newer and more clever ways of developing the attack come, and so on. Okay, so let's look at these defenses in a little bit of detail and sort of see how it works. In fact, I'm going to talk about WXORX and return to libc attacks because it nicely sets up the next lecture, where we are going to talk about a new paradigm for creating these buffer overflow attacks called return-oriented programming. Okay, so let me briefly explain to you what these return to libc attacks are and why they came to be. But before that, before we get to return to libc attacks, I must talk about WXORX, or rather an earlier version of it called non-executable stack. Okay, so what is non-executable stack? Well, it's a defense mechanism. And what is the core idea behind the non-executable stack? Well, it's an operating system level defense that talks about the following, right? So let's go back to this attack that we just saw and see how it worked. So if you look at this attack and see how it worked, the way that the attack worked was that the attacker injected all of his attack payload, which is the executable code he wanted to execute, into the stack buffer over here. That was, it gets placed on the stack, and the return address is going to get modified to the beginning of this attack sequence. So the idea behind this defense is that, is the realization that why should code sit on the stack, right? Code, as you know, in the program's address space, it sits somewhere else in the program's address space, right? It's somewhere else right down below in the program's code region. Code should not be sitting on the stack. The stack is the place for data to sit. You make space for local variables, you pass arguments, you place the return address, but you never place executable code on the stack. There's no reason to do so. Well, in fact, there is reason to do so if you think about things like just-in-time interpreters and so on, which in fact Chrome uses, I believe, for JavaScript. Code is generated all the time at runtime and placed on the stack. But for a minute, let's just forget these variants and let's think about the simple version. You don't need to place code on the stack. So you can take the pages, the operating system pages that correspond to these particular virtual pages and make them non-executable. You can tell the hardware, look, this particular 4K page on which the stack is being placed, there's no reason for this code over here to contain any sort of executable. There's no reason for this page to contain any sort of executable code. So I'm going to remove execute privileges from this page. And the way you specify this is using permission bits on the page table. Okay, so within the operating system, every time you identify a page, a virtual page as being a stack page, the operating system goes and sets the corresponding execute bit for this page table entry to be non-executable. Okay, so it's set to be non-executable. So what happens is that if you go and try to execute that particular page or code sitting in that page, the hardware will throw a fault because, well, that page is not supposed to contain anything executable. And so this is a very widely deployed defense. The hardware obviously has to be modified to have this bit, interpret that bit, and so on. And it's very, very widely deployed. Linux has a defense. Solaris has a defense. OpenBSD has a defense. Everybody has implemented this. It's there in practice now, and it's actually very, very widely applicable. Right? It does break some things. For example, Lisp interpreters, as I said, just-in-time interpreters, they get broken. There are easy ways around it, right? You just go and set the corresponding pages where this code is generated to be executable. But the key thing is that it does not defend against this class of attacks called return to libc exploits. Okay, and it also doesn't defend against heap and function pointer overflows. So let me tell you what these return to libc exploits are. Okay, in fact, next few slides I believe are heap exploits. Let me just skip over that. We'll come back to that later. But let me just explain to you what these return to libc exploits are. We'll come back to heap exploits later. They are just more exotic variants of the stack-based exploits that I spoke about. But what's a return to libc exploit? Well, remember I told you libc is generally loaded into the program's address space of most programs, right? Because they use, even if you were to use something as simple as printf, libc is going to be loaded into your program's address space. Okay, so the main idea behind return to libc exploits is that instead of injecting code into the program during a buffer overflow, you try to execute code that already exists in the program's address space. Okay, so most programs have libc already loaded in memory, and attacks have attempted to execute this code, and that's why it's called return to libc. Although it's become much more general now, you just don't return to libc, rather you use any code that's already there in the program's address space. And we will take this idea of executing any code in the program's address space to its logical extreme in the next lecture. Okay, so what happens over here is that you're just going to take code that's already in the program's address space, change the return address to execute that stuff, and you're done. Okay, so I'll give you the most simple example. So there is a call called system in libc. This should not be confused with the operating system notion of a system call, but rather the system libc call that does the following. So system, this libc call, it takes one string argument, okay, and it just takes that argument that you provide as a string and mimics the effect of running that particular argument on the command line. Okay, so if you want to do, let's say, system and then within quotes you give exec bash, it's going to spawn a shell for you. Okay. Now let's assume that libc is loaded into the program's address space. So this system call over here, quote unquote system library call, the code for this sits somewhere in the program's address space. So now imagine that you wanted to spawn a shell. You are a bad guy, you want to spawn a shell. What do? Well, what you do is you arrange for your buffer overflow to do the following. In your buffer, go and overwrite the return address with the address of the system library call. And on your runtime stack, you go look for where the system library call will go and look for arguments. And over there, you just write down the string exec bash, or rather place a pointer to the string exec bash. So you would fill up the bytes correspond to exec space bash in your injected string. Take the address of this e byte over here, the first byte, and pass that as the argument to system call. Okay, and then you run this. It works, right? You get the same shell without having to undergo the pain of inserting executable code into the stack. So look at the beauty of what we did here, right? On the stack, if you examine, there was not a single piece of executable code that you inserted. All you inserted was data. You inserted the string exec space bash. That's all you did. Okay, you inserted a string. That's what the buffer is there for, to accept strings. You inserted a string and you overwrote the return address to point to the beginning of this string sequence. Sorry, you overwrote the return address to point to the system call, and you passed as an argument the first address of this exec bash. So on the stack, there is no executable code, yet the attack works. Why does it work? Well, you pass data and then you put the program's own code to use against itself. Okay. So you arrange for suitable parameters to be on the stack, that is in this particular case the string exec bash, and then you overwrite the return address with the address of this libc call, which is system. And lo and behold, your attack works. And the key thing over here is that it defeats this non-executable bit, because your stack did not contain any executable code. It just contained data. It's supposed to contain data. It still contains data, and your code is sitting in your code segment, and it still works, right? So what is W XOR X? So W XOR X is just a generic version of this non-executable bit defense. It says that every page in your process virtual address space can either have write permission or execute permission, but not both. That's why you have this XOR, right? If you have write permissions, it means that you wrote to the page. It must be a data page. It cannot contain code. If you have given executable permissions, that means that that page contains code. You should not write any data to it. Okay, so that's why it's called W XOR X. That's just a more general version of applying this non-executable bit defense. And the key thing is that return to libc exploits neatly exploit this sort of bypass this W XOR X difference. Okay, all right. So the key is that until 2007 or so, this return to libc attacks were considered feasible. It was shown the feasibility was possible. The feasibility was established, but it was considered a relatively exotic attack. Some guy in the hacker world demonstrated it in their sort of a blog or whatever they have. And W XOR X was pretty much considered to be an effective defense for a large majority of known exploits. Okay, but what I will show in the next class is something called return-oriented programming, which is a systematic way to put the program's code to bad use against itself, and it significantly changed this perspective of whether W XOR X is an effective defense at all. Okay, and it's forced the community to rethink operating system level defenses against buffer overflow attacks. Okay, so next class we'll talk about return to libc exploits. Return oriented programming, and we will sort of see how it works. So next slide and so on are return oriented programming. What I want to do, I've got 15 more minutes remaining. Let me talk about some other basic defenses against buffer overflow attacks, and we will stop over there, okay, for today. And we will, in fact, the rest of this month is going to be devoted to defenses. What I want to do is to give you a breadth first overview of the various kinds of defenses. So let me sort of cover that now. So of course, one easy way to defend against buffer overflows is to use safe programming languages like Java. But that, of course, there's a lot of legacy C code, and you cannot really defend against exploits against these legacy programs. There's black box testing with long strings, which is first testing that I spoke about. At least you can find the buffer overflows. Marking stack non-executable, we just went over this defense. There is randomizing stack location, which is ASLR. I will talk about it in detail. So what this does is that this adds some non-determinism, right? So every instance of the program, when you start it, the base address of the stack is going to be different. So the return address is not going to be at the same location. So the attacker, if you create an attack at home with a replica of the vulnerable program and you create an exploit, that exploit is not going to work on another instance of the program because the program looks different. The stack has been offset by a random amount. We'll talk about this in a little bit of detail. And there are other runtime checking techniques, one of which I'm going to describe now, right? It's actually a very, very popular defense. Let me just set this PowerPoint stuff over here. PowerPoint has messed it up. Let me just set that up and then we can continue. Okay. Oops. Okay. All right. Let me just. Okay. So this particular defense, as I fix this, let me start explaining. So this is a particular defense called stack canaries. So in fact, the stack canary based defense is very widely deployed. It's also available in GCC almost by default, to the extent that if you want to disable it, I think you have to use an option called -F no stack canary. But it's a defense that compiles programs and prevents certain kinds of buffer overflows. I will present the defense. Next class we'll start with a discussion of what it cannot prevent. So what I want you to do is to go home and think about this defense and see whether it's a perfect defense. Okay, so let's talk about it. So this slide over here, the picture is drawn slightly differently. I've taken the stack is now sort of very tired after having done all this work to explain to you how it works. So now it's lying down. Okay, so the top of the stack is over here and the bottom of the stack is over here, moves that way. Okay, so that's how this is. Well, so as you can see over here, here's your main function, here may be your foo, and here is the local buffer over here. Okay, so, and there's the return address and there's the same frame pointer. The defense works basically by placing what's called a canary value between the buffer and the return address. Okay, so what's a canary? A canary is a random 4-byte value that you place over here on the stack. And you also save this canary value somewhere else on a page. And you remove write permissions from the page. You save it there, remove write permissions. Every time you want to write to that page, you would actually set write permissions for that page, write the canary value, and then remove the write permissions for that page. Okay, and so the basic idea behind the canary is that every time you invoke a function, a random value is placed between the return address and the stack frame for that function. And whenever the function returns, you're going to check that the canary value over here matches what is there in the saved page. Okay. And if there's a mismatch, you declare that an attack has happened. Why is this what's the rationale behind this defense? Well, the idea is that if there is a buffer overflow of the type that we spoke about, a stack-based buffer overflow that works in the way that I spoke about, that the attacker would have injected stuff into this buffer, done a linear write over this buffer, overwriting the canary before overwriting the return address. Okay, so if the return address was overwritten, perhaps this canary is also overwritten. And if you have a good enough random number generator, your attacker is not able to guess the random value that you placed over here. Therefore, if your canary is mismatching what you saved somewhere else on the program stack, an attack must have happened. Okay, that's the idea behind this defense. Okay. So of course, you might have different questions, some of which are technical. Of course, we'll discuss that in the next class. Why does this defense work, or rather, why does it not work? That's what I want you to think about. Why does it not work? But of course, the most pressing question at this point is, why is it called a canary? right? So the reason it's called a canary is actually a very interesting story. Goes back to coal miners in the early part of last century. Apparently, when they used to go down to the coal mines and when technology was not as well developed to have sensors for gas detectors and so on, what is the thing that's most dangerous in a coal mine? Of course, there's the danger of the coal mine collapsing. That's of course always there. But the more dangerous thing about the coal mine is that it's all carbon, right? So when carbon can mix with oxygen, of course, it produces carbon dioxide, which is dangerous but not lethal. But there's carbon monoxide, which is actually lethal, the sense that it's odorless and it immediately kills. Okay, and in a coal mine, you have the risk of carbon monoxide poisoning. Okay, the problem is that these miners, they cannot really detect if they are being poisoned by carbon monoxide because carbon monoxide does not have any odor. Okay, so how do you detect carbon monoxide? Well, legend has it that they used to take down a canary, small bird in a cage, and sort of tie it to the roof where they're working, and the canary keeps singing. It's a bird that keeps singing. Okay, and the minute the canary stops singing, they sort of see, hey, why is it stopped singing? It has dropped dead. It's a small bird, right? Little bit of carbon monoxide kills the canary, and the minute the canary is dead, they know they have to run out of the mine. Okay, it's evil of the canary, poor canary. I feel sorry for it. But the idea is that that's why it's called a canary-based defense. As soon as this canary here starts singing, this case starts singing, right, where the canary value doesn't match what is there in the saved page, you know that there is an attack and you quit the program. Okay, so it's called stack canaries. It's a very, very popular defense. It's there in GCC. All modern compilers have some version of it. Next class, I want you to think about why don't canaries work. We will start here. Okay, so I realize I've moved around a little bit in the slides, but I wanted the logical flow of things before I tell you about heap-based buffer overflows and so on much later in the semester. So we'll stop here today. I will take 5 minutes worth of questions and we will sort of I want you guys to think about why stack canaries may not work, what are ways to defeat it, and so on. Let's take some questions. I have one question from Shaukat Ali. Please go ahead, Shaukat.
Yes, sir. Am I audible?
Yes, you are.
In this canary-based attack, sir, is it necessary that we write over the this canary byte? Because in the first program that you showed, we
Yes.
wrote over that return address without overwriting the bytes in between. We just went to the buffer address and then added the whatever byte
No, that's
addresses
not
we
true.
needed.
That's not true. In the attack that I showed, we did override everything intervening. Right?
In the
So
first program,
yeah, the toy program you mean?
yeah,
That
toy program
stack,
where you just update it to the
true.
buffer.
But hey, but that was a toy program, and I wrote the code to actually override the return address. Can you think about how you would do it if you're given a buffer and a getter statement, and then override the return address without overriding the canary? You have a very good point. But what I'm saying is, don't look at that benign return address program that I showed the virtual machine. Think about the setup where you have a buffer, a stack-based buffer, and a getter statement, and then think about if you can serially override that buffer without overriding the canary. I want to go and override the return address. If you can show me, you've got the answer to the question that I just asked, which is, how can you defeat stack canaries? But that first program is not a valid attack because, I wrote the attack right over there. It was like a benign program where I set it up so that the return address is there and I went and modified it. I want you to sort of mimic the same kind of attack that I just showed, the payload engineering part, and then show me how you can override the return address with the without overriding the canary. If you can show me this, then you have the answer to the question. So that's a challenge for you. Yeah. Somebody else has a question. I can't.
We can't, sir.
Yeah, please.
Yes, sir. We can use stack base pointer for avoiding writing canaries.
You can use stack-based pointer. What does that mean?
Means we can write buffer and then write from stack base pointer up to the point we want.
Stack-based pointer. You mean ESP?
EBP. EBP.
You can use EBP. How would you do it in a buffer overflow? See, when you're going to get a getter statement or something like this, you have to fill up the buffer serially. how would you use ESP or EBP? You have to think about overwriting it pretty much from the command line or from the network, right? So you have to give me the precise formula over there of how you would do it, right? ESP and EBP are registers in the program. How would you overwrite it without overwriting the canary?
So we can write starting from EPP after writing buffer.
After writing the
Or
buffer. But how would you skip over the canary bytes?
Sir, I think we should stress on a point that we should take the program as a black box. We cannot change anything what is there except for giving the inputs.
Exactly.
So I think that is the point that people are missing.
Yes, yes. The
Yeah.
program is a black box. You cannot change the program. You just have, imagine that this vulnerable program is running and you are able to feed inputs from the command line. You cannot change the code of the program. You just have to write into this buffer and somehow override the return address without overriding the canary. If you can show me that that is possible, then you have defeated stack-based stack canaries. Okay, so that's a challenge to you guys, right? So sort of think about how you would do it. I can tell you that you can do it because obviously this defense has been defeated. But I want you to give some thought to it. So all of the defenses I've heard so far involve changing the program and so on. You cannot do that, as this person who just commented rightly pointed out. The program is a black box. You cannot modify it. You can just feed input to it, and you have to accomplish this task without changing the canary. Okay. So further questions? All right. So if not, let us call an end to this class. And next class, I will start off with an overview of these various defenses. And I will tell you about this really exciting development called return-oriented programming. In fact, the cat and mouse game for return-oriented programming continues to this day. If you go and if you go and look at the program for one of the recent security research conferences, you will probably find at least 2 or 3 papers on return-oriented programming. And how to make it even more sophisticated and defenses against this and so on. Okay, so it's a really, really sort of exciting and really out of the box way of thinking about buffer overflow exploits, and you will see it next class in action. All right, so that's it for today. Thank you.